Um, any questions about what we talked about last time? Did the chapter seem relatively straightforward? Okay. One thing we didn't get to before we start messing with regression, one thing we didn't get to was the last slide. I'll get rid of this. The last slide on the last presentation is just too much of a pain to bring it up on iTunes, on PowerPoint on the iPad, is this idea of adaptation. Adaptation, I think, is confusing to you guys. And the reason that it's confusing is that biologists, evolutionary biologists, ecologists, behavioral ecologists, all of us have been doing a terrible job at describing what an adaptation is, in that we tend to ascribe adaptive value to practically everything. And there was a guy named Stephen Jay Gould at Harvard who took it upon himself to try and single-handedly break biologists of this habit that we have of what he refers to as adaptive storytelling. We see a particular characteristic or a particular behavior or something like that of an organism, and then we create some adaptive story that accounts for why evolution would have crafted that characteristic or behavior or whatever else. And so he wrote a series of papers, and if you go to graduate school, you might read them. If you took an evolution class, you might read them. He wrote a series of papers, both himself and a guy named Niles Eldredge, and a woman named, I think her first name was Sarah Verba, basically outlining a more rigid definition for what an adaptation is. And their criteria were that an adaptation was any characteristic, and whenever I use the term characteristic, it could be a morphological characteristic, it could be a behavioral characteristic, it could be a physiological characteristic, any trait that increases fitness was shaped by the force of natural selection. And the thing that I think most people objected to when they put out this definition was for its current purpose. And so this is a really, really narrow definition of what an adaptation is. A looser definition would be any characteristic that increases fitness, regardless of whether it was shaped by natural selection or not, and regardless of whether natural selection shaped it for its current purpose. So for example, I think I forgot to bring one, but, oh, yeah, I did. I forgot my one visual aid because I don't like bringing it to class with me. How many of you have a cell phone? Pull out your cell phone. Text a text to your significant other asking them if they want to hook up with you later on this afternoon or this evening. Okay, don't do that. Don't do that. But the fact of the matter is, you could. What do you normally text with? Your thumbs. So, can your thumb increase your fitness by texting? I mean, if you have somebody to text, sure it could. Did your thumb evolve to text? It didn't, no, because you had a thumb long before we had cell phones. So there's no way that your thumb evolved to text. Even though texting might improve your fitness, that wasn't the purpose by which natural selection favored its evolution. So the thumb is an adaptation. What is it an adaptation for? Yeah, the primary function is believed just it improves your grip. Ever try hanging onto something without using your thumb? Ever swing a bat? Who swings a bat this way with the thumb out here like this? Because you swing the bat, and what do you not have? You don't have a firm grip on it. wrap your thumb around it, and you've got a firm grip, which is important for things that are going to hang on to tree branches, for example. Anybody ever look at gymnasts? Is anybody a gymnast in here? Take gymnastics when you were younger?
Younger.
You guys ever do the parallel bars?
Oh, yeah.
How do you grip the parallel bar? Do you use your thumb?
Well, I don't remember. I was like 6.
Yeah, you did.
Do you?
Yeah, I think so.
How do you dismount with your thumb over there? You just let it go at the last minute?
Yeah.
Yeah, okay.
Yeah.
Thumb gives you a firmer grip on things. It also allows you to use tools eventually when you start developing tools. It allows you to thumb your nose at people. It allows you to do a great many things once you have it, but the purpose, presumably, that got you there originally was grasping.
Isn't there a huge debate over feathers in this aspect?
By a huge debate, you mean were they originally evolved for flight or for thermoregulation?
Right.
I don't know. I've never heard that before. Yeah, so there's a debate as to whether or not feathers are an adaptation for flight. And if you apply this really narrow definition, that becomes a really important question, because if they originally became a fitness enhancing characteristic or trait for the early reptiles that eventually evolved into birds, and that early use in gaining fitness was for thermoregulation, then they're not an adaptation to flight. They're an adaptation for maintaining body temperature. But that's assuming that you apply this really narrow definition. And people would sometimes like to not apply that narrow definition, because one of the things that they are very useful for is, of course, what? Flight. Birds fly. And so this is the part of that definition that gets the most grief. Yeah, Isaac, you have a question?
Yeah. So if feathers were originally an adaptation for thermoregulation, but those were early feathers, and then modern feathers were further shaped by natural selection to be better for flight, would then the modern feathers nevertheless be an adaptation for flight?
This is why I'm exposing you to the idea, but not belaboring the point. So if feathers were originally developed, originally came into being and increased the fitness of birds because they helped them retain body heat, and then were later co-opted for flight, chances are these kinds of feathers are going to have a different shape than these kinds of feathers, because flight feathers are not particularly good. I mean, they are good to a point, but there are better feather designs that are better at maintaining body temperature, and those are the downy feathers. And of course, who gets downy feathers? Baby birds. Baby birds, they have really small body size. They shed a lot of heat because they're really small and there's a lot of surface area, and so they're just constantly shedding heat to the environment. Downy feathers are very good at retaining body heat. Flight feathers, which are the ones that grow in after the downy feathers are molted, are good for what? Flight feathers. And so, in this case, birds actually have two different kinds of feathers that change ontogenetically from down feathers to flight feathers. And they have totally different shapes, and those shapes are reflected by their function. So, for the purpose of this course, we're just going to say, well, we're going to go a little simpler and say it's something that improves fitness, and improves fitness because it was shaped by natural selection. Whether that's a structure that was co-opted from some other structure that had some other utility in the past or not, I don't really care, because when we're studying organisms right now, all we can really see is current utility. Because we don't have a time machine, we can't go back in time and figure out what those earlier utilities were. You want to share
I
something?
was just going to ask you, I walked in as you were explaining this. You've written Gould there.
Yes.
Gould and Lowenton argued against this kind of adaptationist thinking, though, yes? They're the ones that wrote the Spandrels of San Marcos. Yeah.
Gould, yeah, so they're the ones who are arguing against applying adaptive. I talked about this before we walked in, I guess. They argued against creating adaptationist stories to account for every characteristic that an organism has. And the reason is that we got in a bad habit of doing this, and not every trait that you have is going to increase your fitness, and there are tons of traits that you have that are just kind of neutral. They're hanging around because they don't really serve any purpose in terms of increasing fitness, but they also don't decrease your fitness. And in many cases, you have a lot of traits that are just being drug along by other traits. We're going to talk about some of those. Is that the point you're trying to make, or?
Yeah, I just, because it was written for its current purpose with his name, I don't know if he ascribes that definition or not.
A paper in the American Naturalist in 1982. The definitions in the PowerPoint are from that paper, and so they take a very narrow view of adaptation in that paper, and then they say everything else should be spoken of as an exaptation. And I'm not going to ask you to know exaptation. Just know that adaptive traits are generally those traits that increase fitness, and because they increase fitness, chances are they got to be that way because they were shaped by natural selection of one type or another. Does that work for you?
Yeah, that's good.
So that's the last thing that I wanted to cover. What we're studying in this case study are two types of adaptation, and we would think of them as adaptations. One is the development of tetrodotoxin by newts that render predators immobilized because they block sodium channels. And then in some predators, those predators have evolved resistance to tetrodotoxin, such that tetrodotoxin doesn't block their sodium channels quite as well, and so they're not immobilized. And it's really easy to see how in that interaction, those two things are both an anti-predator adaptation on the part of the newt and an anti-prey defense adaptation on the part of the snake. And so these are both characteristics that increase fitness and are certainly probably subject to natural selection. And so just wanted to cover that last slide. Questions about that? You don't have to listen to Stephen Jay Gould just because he's Stephen Jay Gould.
A lot of people don't.
Well, a lot of people don't. A lot of people don't.
Vociferously do not.
Yeah. He was a polarizing figure in evolutionary biology.
Oh, yeah,
Hmm? What's that?
I mean, like, he's cool, like, it was fun having him around.
Yeah, he pushed boundaries and pushed people to think harder about things. He also had a really nice way of writing. If you ever want to read a paper that is really good at using analogies in science writing, the title of the paper is Homage to Santa Rosalia, I think. No, the Spandrels of San Marco, sorry.
Oh, I didn't know which one you were talking about.
The Spandrels of San Marco is a good paper if you ever want to just read a paper that has a good analogy. It's not about architectural features in medieval churches, but it uses that as an analogy for people creating adaptive stories. All right. In the papers that you're going to be reading, there is a lot of linear regression analysis in those papers. And so at the beginning of every case study, we take you through the statistical methods that are going to be used, at least the primary ones that jump out at us. And for this case study, it is regression. Regression is simply when we estimate the relationship of one continuous variable with another by expressing one in terms of a linear or more complex function of the other. This should be fairly familiar to you. Oftentimes, though, you guys think in terms of correlation, just the degree to which two variables co-vary with one another. And so there's a slight distinction. Correlation measures association. Presumably, regression measures causation. And I'll explain what the difference is between that here in a minute. So we generally think of this as taking the form of a line. You might have, I was exposed to this line as y equals mx plus b, where m is the slope. But you could put, in theory, anything in here. Most people nowadays use beta if you're taking a statistics class. And so it would be that form there where A is the y-intercept, B is a lowercase form of beta, and that's the slope value. But it's basically y equals slope times the x value plus the y-intercept. So there are two types of regressions, and well, actually there are way more than two types, but there are two main categories of regression. The first one of these is called the ordinary least squares regression, or some people refer to it as Model 1 regression. This is the kind of regression that basically everybody who ever runs a regression does. There are some weird, freaky people who don't do this, but most, Dr. Reynolds is wrinkling her nose. I would say the vast majority of biologists, when they run a regression, they run this, whether they should be doing it or not. And the reason that you shouldn't be doing it is because the situations under which you can do this are really, really narrow. It assumes that you have an independent variable x, which is measured without error. And it also assumes that that variable is under the control of the investigator. And so you, the investigator, set what x is, and then you look to see how y responds to that experimental manipulation of x. It's fixed, and it's under the control of the investigator. And then you look and see what is the expected response in the y variable. And so in this way, regression is nice because it is causal. I did something to x, and when I did that to x, y responded in a particular way. So regression, especially if it's Model 1, is much more causal than simply correlation. Because you, the investigator, are manipulating the x variable. There are normality assumptions and homogeneity of variance assumptions and all that, just like there are for analysis of variance. But these are the big things for ordinary least square regression. There's another type of regression called Model 2 regression. And in this case, both x and y are random variables. You, the investigator, are not controlling them. They can be whatever. You're just measuring x, and then something corresponding to x, y, you're also measuring, and you're seeing how those things are related. And this is referred to as Model 2 or standard major axis, or reduced major axis, or geometric mean regression. There are lots of models that do the same kind of regression. But you should do these other types when you don't have control over x. And seldom do you have control over x. How many of you have used regression for your lab project? At least 2 groups have. In those cases, did you have any control over the x variable? No, you didn't. You just observed the x variable, and then you observed some y variable, and you're looking for an association between those two. Aside from the fact that we shouldn't do it this way, we're going to do it this way because this is the way it's done in your papers, the ordinary least squares regression or Model 1 regression. So this is an example from a textbook. They took some flower beetles, the confused flower beetle. They raised them under different conditions of relative humidity, which were set by the investigator, although one would think that they would have done a better job of setting the humidities than they did. And then they weighed the beetles in 9 groups of 25 beetles apiece, and then they weighed them again 6 days later to see what kind of weight they lost or gained. The independent variable here is relative humidity, and then that is presumably affecting weight loss or weight gain, which is the dependent variable. And this is what the data look like. It's a little tiny data set, but one of the nice things about tiny data sets is you can see things more easily. And this is what it looks like if you graph relative humidity versus weight loss, and it's just a graph of this thing. So it would be nice if they had a different sort of more standard sort of range of humidities, but this is probably what they could achieve in the lab. What happens as you reduce relative humidity? What happens to weight loss? Yeah, weight loss increases as you get lower and lower humidity. Higher and higher humidity, you have less weight loss over the 6 days. Well, you can, when you test a regression, you're basically testing the hypothesis that the slope is equal to 0 versus the alternative hypothesis that the slope is either, well, it's either less than or greater than 0, not equal to 0. It's either a positive slope or a negative slope. You're not testing, generally speaking, where the y-intercept is to see if the y-intercept is different from 0. Most people who are testing regressions are testing to see if the relationship is significant, and so that's a slope question. And so you could actually average all of the weight losses, arrive at that average, and just plot a flat line, a line with a slope of 0 that goes through the average weight loss of the beetles, and that's your null hypothesis. And you're testing to see if this data set has a slope that's different from the null hypothesis. Do you think it has a slope different from the null hypothesis? Yeah, sure it does. Because these data points out here and out here are pretty far from that line. The distance between the hypothesized line and the data points in the y-axis direction, these things are referred to as residuals. And so as you're reading the Brody and Brody paper, they're going to talk about residual speed. And so snakes, garter snakes in particular, are peculiar in that they're unlike us in that they don't have limbs, for starters. But what they do have is they have a really long backbone. And the length of the snake is due to the number of vertebrae that they have in their backbone. And it turns out that the belly scales on the underside of the snake have a 1-to-1 correspondent with the vertebrae that are in the snake. And a guy named Stephen Arnold figured out that these vertebral counts vary within a quantitative genetic sort of way. So they have a normal sort of distribution. You have some snakes that are very long, some snakes that are pretty short, and a bunch of snakes that are kind of average in the middle. And that is determined by the genes that they got that determine vertebral number from their parents. And the longer the snake equals more vertebrae, and that equals faster. The more vertebrae you have, the faster you are. The longer you are, the faster you are. And so one of the things that you want to do is, because the length of the snake is related to the speed of the snake in pretty much a linear sort of fashion, some of these snakes are faster than other snakes simply because they're longer. And so one of the things that you might want to do is you might want to correct and say, well, what is the length specific speed of a snake? Well, one of the ways you can do that is you can say, well, in this range of sizes, some of these guys are fast and some of these guys are relatively slow, even though they're about the same length. And so one of the things you can use residuals for is correcting for body size in things like this, and that's one of the things that the Brodies use this for, because they're dealing with snakes and they're measuring speed. But the other thing that residuals are used for is for figuring out what line is the appropriate line, because what they're going to basically do is take this line and tilt it at the mean of the x values, and they're going to tilt it until you've minimized all of the residuals. And so they're basically going to take this line, tilt it, and now all of a sudden the distance between the points on the line are really small, and the correct slope that is the best fit line is the slope of the line that reduces the amount of these residuals across the whole data set. And so it's another kind of sums of squares sort of thing. The line itself represents the running average of weight loss as you go across all of the x variables, and the residuals are the deviations from that average. And so it's not really any different than running an ANOVA. It's just that you're running an ANOVA on data that varies with another variable. Yeah.
So Steve, would it be fair to summarize this by saying that, like, for example, in your speed and length example, you're basically just taking, you're controlling for the speed that is gained by length so that you can look at the variation, the remaining variation?
Yep. So that's what the Brodies are doing. That's how they're using residuals. The reason we're using residuals here is to tell us what line is appropriate. But yeah, so in that same way, another way of thinking about this is what if we said this is the average X value. If we moved all of these data points down parallel to the slope of the line to the X value and moved all of these up, now everybody's the same length. What would their relative speeds be at that length is another way of thinking about what the Brodies are doing.
This is a two-dimensional principal complement, so you're taking out the correlation between.
Yes, if you want to think of it that way, sure. Principal component analysis actually is just a really complicated set of regressions in reality.
Asa, did you have a question?
Yes.
Oh yeah, sorry.
According to the line of baskets reduces the residual values. Do you mean the residuals below the line or above?
All of them. So when we tilt this line from flat, it's going to reduce, we're going to raise it on this side, which reduces the residuals over here, and we're going to lower it on this side, which reduces the residuals here. And so it does both at the same time. And then whatever the slope of the line is that rocks. So there's an average X value. Think of it as a fulcrum on a teeter-totter, and you can literally just tip the line, and you tip it until the line reduces the total residuals across the whole data set to their minimum value. And so that's what it's doing. Yeah.
I read from the book, they say if you have three of the residuals that are like that correlates, you can draw a line on the passage through those three residuals. Is that valid?
You have three ones?
Like if you have three residuals that correlates, you could draw a line on the passage through that. Is that valid?
I don't know about three, but I have
So
two.
like for this, you just say if you can find like three of the points that are in correlation, linear form, you just draw your line of passage through them.
No, because you would be ignoring all the rest of them. You need the whole data set if I'm understanding because in theory, you could find a number of points that you could draw a line through exactly. And in some data sets, you're never going to find a set of three values that you can draw a line through directly.
So for example, the middle three, here you could draw a straight line that would go flat across, but that would not be representative of the residuals here.
And also, just because these three look like they're all on the same line, it's part of that is obscuring variation among those from the line because the marker is a certain size. If I made that marker really small, they might be slightly off of the line. The only thing that you can really get a reliable line between is 2 points in most data. It's really hard to find three naturally derived points that you could get a perfect line through, depending on your precision of measurement. The more precise you're measuring things, actually, the more difficult it becomes. Rose, you had something else? You look like you did.
No,
Okay. So this is a simple example. It gives you a equation for the line. The y value is determined by the slope, which in this case is negative, the x value, whatever the x value is, and the y-intercept. And the y-intercept is way up there, partly because this thing has a negative slope. But when you go to test this using regression analysis, you're not testing to see if the y-intercept is different from 0. You're testing to see if the slope value is different from 0. And then there's this r-squared value that I think is really pretty important. R-squared is sometimes referred to as the coefficient of determination, which means nothing to you, and I realize that. One way of thinking about this, and I think it's one of the more productive ways of thinking about this at the beginning when you don't really know that much about statistics, is basically saying how much of the variation in the y variable is explained by variation in the x variable. In this data set, if you know something about x, what do you know about y? Quite a lot or not very much? You know quite a bit, because the line does a really good job of describing the data set, and there's not a lot of variation around the line. And so you have an r-squared that's really high, close to 1, which basically tells you that the x variable tells you quite a lot of information about what's happening with the y variable. The residuals are now really small. R-squared, this would be an r-squared of 1, where every point lies on the line. If you know something about x, what do you know about y? Everything there is to know about y. In this situation, if you know about x, what do you also know about y? You know quite a lot, r.9, but you don't know as much about y as you did in this situation. In this case, if you know about x, what do you know about y?
Some.
Yeah, you know less than you did in either of the other situations. And so your r-squared is down at about 0.7. And if you get really sloppy with the data really aren't described very well by x at all, knowing something about x really doesn't tell you much about y at all. And in this case, the r-squared value is down at 0.43. And so r-squared is a measure of the spread of the data around that line, because as that spread gets wider and wider, x is telling you less and less about y. It's explaining less and less of the variation. Yeah, Asa.
How do you calculate the r-squared?
Hmm?
How do you calculate the r-squared?
Take an applied statistics class and we'll go through and work it out by hand.
It's a little complicated.
Regressions are actually harder, way harder than de novos to calculate, and it would take the rest of the class to go through the calculations of doing this.
Sorry.
But I can take it through you sometime if you really want to know. My advice would be go take a stats class and learn about it if you're that interested. Here's some real data. When I first saw this paper when I was a graduate student, I went, no way. So this is from a guy who works on barn swallows. And he's looking at barn swallow female tail length and male tail length. And he's making the argument that these things are under selection from female choice because the female tail length and the male tail length are correlated with one another. What do you notice about this particular regression? It seems really messy, doesn't it? What else do you notice about it? Asa.
He had a lot of data. Right?
He has a ton of data, doesn't he? So when I see a figure like this, when I see any regression, I look down in the figure. And so this is a decent figure. Figure 6, tail length of female barn swallows in relation to the tail length of their mates. Then it tells you what A and B are. Absolute tail length. The regression equation is female tail length. So let's do this. Female tail length is equal to 68.96 plus 0.17 times male tail length. Does that strike you as a very large slope value? It doesn't me either, and it doesn't to look at the number itself, and it also doesn't looking at the figure. But then you go down here and you look at the F statistic. The F statistic for this regression is 33.05, which that's a huge F statistic. But the R-squared value is 0.09, which strikes me as a really small amount of information. It's basically telling you that knowing something about X doesn't really tell you much about Y. And when you look at the statistics of this F statistic is significant at a p-value of 0.001. I'm sorry, 0.0001. I missed a 0 there. Which means that if you say that the slope is different from 0, there's practically no chance that you're going to be wrong. So it's saying that the slope is different from 0. It really doesn't explain much about the relationship between female tail length and male tail length. Well, how can those two things both be true? He has tons of degrees of freedom. He has 338 breeding pairs that are in this analysis. So he's crushed this regression with sample size. And give me enough sample size, and I can show you a difference between things that are really, really, really similar to one another. And so that's one of the dangers, actually, of regression, is you can get things that are statistically significant that may or may not be biologically significant if you crush it with a big enough sample size. And I would argue that this is one of those situations where that's the case. You have tons of sample size supporting a significant regression, that slope is different from 0, that isn't really all that informative. And we should try and avoid publishing those kinds of things in the journal Evolution. Yeah, Asa.
Is there a reason why he or she decided to use small samples?
Oh yeah, so these circles are different sizes depending on how many data points happen to land at the same spot. So the circles are bigger when you have more observations at the same point, and they're smaller when you don't. It's a common way of when you have a lot of data of overlapping things, so that you can show where the body of your sample exists. Does everybody understand what my issue is with this particular set of plots?
Yeah, I think just looking at the graph, my attempt is to think maybe there's no correlation or like a positive or negative. It's kind of about it.
Yeah, so are you asking about residuals?
Just like comment on the graph, like without the calculations of the values, the degrees of freedom, the S statistics and all that, and without the line, just looking at the data itself, some might be tempted to think that maybe there's no correlation at all.
Yeah, it's if the line weren't there and you didn't have the statistical results in the caption, you might just look at that thing and see that as kind of a random cloud of points. But it is statistically different than a slope of 0. So remember from when Dr. Reynolds was talking to you guys about evolution and she talked about heritability, we can use regression to measure heritability if we have the phenotypes of parents and the phenotypes of offspring. Just run a regression line through that. And in this case, the phenotype of the parents is having a causative effect, or the genes underlying their phenotype are having a causative effect on the phenotype of the offspring. And so ordinary least squares regression is appropriate, and the slope of the line gives you an estimate of heritability. I wanted to give you a bigger data set that kind of illustrates what the Brodies are doing when they measure residual sprint speed and things like this. So I downloaded a data set off of the web that's 408 observations of the height of humans and their shoe size. And the question that the data set was attempting to address is, do men and women have different shoe sizes? And we would typically analyze this using an ANOVA. We would look at shoe size. We would have a categorization variable, male and female, which represents gender. And we would just basically do an analysis of variance on shoe size. And what do we find? What's that?
They're different.
Yeah, Caitlin says they're different. Men have way bigger feet than women. Why?
It's usually bigger.
Dudes are generally taller than females in human populations. And so you can't just look at this difference in shoe size and say, men have bigger shoe sizes than women, when you know that out there is this correlation that shows that as men get taller, their shoe size gets bigger. Now, Asa, back to your question, there are lots of overlapping points at each of these because remember there's 408 observations in here. I could have made my circles to reflect how many observations are sitting at this point or how many observations are sitting at this point. There's nothing wrong with that. It's just I didn't take the time to do that with this particular graphic. What do you guys notice about this figure? Somebody other than Isaac and Asa. It should be obvious. I color-coded it for you. Speak up.
The men are taller than 30 feet.
Yeah, so all of the blue circles, which are men, are over here, and all of the red circles, which are women, are down here. And that's because we're sexually dimorphic in terms of height. And so that basically explains, at least in part, what the difference is in shoe size that we observe when we do an analysis of variance. Isaac, you have a question.
Yeah, what's that gray halo thing around?
Oh, that's the 95% confidence interval of the slope. So this is your estimate of the best fit line. Slopes can have 95% confidence intervals in the same way that a mean can have a 95% confidence interval. Remember earlier, I basically said the line is essentially the running average of the y variable as you move across the x variable. And so this is just showing you the 95% confidence interval. And you can see that that's a fairly tight interval. You can't move that line around much inside of that gray area before you're outside the gray area. If it was not significant, you would have a big band going through the middle, and even though the best fit line might be different than a slope of 0, you could move the line around such that you could achieve a slope of 0 while still staying in the gray bands. So it's just the 95% confidence interval. And in this particular package, they display it with gray shading on either side. So how can we correct for this and get a truer view of what the true difference is between male and female shoe size?
Take samples of men and women that are the same height.
Okay, so you could do that. You could say, okay, we're going to pick men and women here in the middle, and we're going to say, these people are all the same height. What are their shoe sizes? Is there a way that we can address it with this data set? Somebody other than Isaac. I've talked about it before, earlier today. Photosynthesizers. All right, yeah, go.
Model 2 regression?
No, presumably, well, we didn't have control over the height, but we probably measured it without any error. In your groups, go back a couple of slides and see if you can find the answer. Talk about it in your groups. 2 minutes. How can we address whether male and female really have different shoe sizes by removing the effect of overall height from the equation? How can we come up with a height-independent measure of shoe size? It's not there. It went back too far. Oh, it looks weird. Open it up in PowerPoint. How can we do this? What? Say it louder. See, you photosynthesize, you know the answer, and you just don't tell me what the answer is. We can basically calculate the residuals. The residual for this female is really small because she's close to the line. It's bigger for this female and negative because she's far below the line. It's really big for this individual because she's way below the line, but it's really big for this male because he's way above the line. For every combination, for every individual, we have height and we have shoe size. Once we know what the regression line is, we can calculate the residual, save those residuals, and those residuals are basically telling you how far away you are from the line, below the line and above the line. So it's like a size-specific measure of shoe size, a height-specific, or a height-independent measure of shoe size. And when we do that, what do you find? Compare this figure to this figure. This figure looks like shoe sizes. Size 8, size 9, size 10, size 11. Man, those dudes have big feet. Those are the shoe sizes. We run the regression, we realize that shoe size is correlated with height. We look at the residuals, save those residuals, and then do an analysis of variance on those residuals. Is this now shoe size any longer? No, it's the distance from the line in shoe size terms. It's the residual shoe size. And what do you notice about shoe size in males and females?
It's still different.
It's still different, but is it as big of a difference as it was before? No, because it removed the complicating effect of overall height. And so they're still different. Notice how they're on both sides of 0, because what's 0 in this case? 0 is the line. If you're exactly on the line, you have a residual value of 0. If you're below the line, you're negative. If you're above the line, you're positive. So this is one of the ways that we can use regression, is to provide data that aren't complicated by effects of body size. And it's a pretty common way in which some types of biologists use regression. And it is rife within the Brody papers. Matter of fact, the first Brody paper that you read is going to use percentages. It's going to use percentage of baseline speed. And between that paper and the next paper that they publish, they read a paper produced by 2 people, Packard and Boardman, that basically say you shouldn't use percentages because percentages are poorly behaved. And so they start using residuals instead. So, question about this. All right, let's talk some actual data. So this isn't in the first paper that you read, this is in the second paper you read. But one of the things that they do throughout the early papers that they published on this is they would take a snake from the field, they would put it in a racetrack, and they would race it down the racetrack, and the racetrack would record the speed that the snake was running at. And then they would inject the snake with a set amount of tetrodotoxin, and then they would measure its speed after it was injected with tetrodotoxin. And what they're doing in these plots is they're plotting different regressions. This is the regression. The dark line is the regression of baseline speed, which is before injection, and post-injection speed, which is after injection. And they have this for every snake that they used. And so they can plot a regression, they can calculate a regression that relates baseline speed to post-injection speed. And what they find is that the slope is always less than 1. And so the dotted line here is less than 1. And when they do that, they basically claim that there's a trade-off between tetrodotoxin resistance and the baseline speed. What they're basically saying is the faster you are, the less resistant you are. Because if there was no trade-off, everybody would be at a 1-to-1 sort of relationship. You might have overall reduced speed, but fast snakes aren't reduced any more than slow snakes are. So what I want to do is I want to show you how this works so that if you get to this paper over the Thanksgiving holidays, which you should probably be working on, you can figure out what's going on. So if we have baseline speed and post-injection speed, if there's no effect of the toxin on their speed, we would just expect snakes that run at 5 meters per second will run at 5 meters per second. If they run at 10 meters per second, they'll run at 10 meters per second. So this should be a 45-degree slope running through the origin. A snake that runs 0 meters per second will run at 0 meters per second. And so that's no effective TTX, and there's no trade-off. So a slope of 1, essentially. If there is an effective tetrodotoxin, you would just expect this whole line to shift down, but still be parallel to the original line, because there's an overall effect, but it affects slow snakes at the same rate that it affects, it has the same effect as it affects fast snakes. But if there's a trade-off, it basically means that fast snakes are affected more than slow snakes are. And so one of the things that you could do is you could find the average X value, find the average Y value, and plot those there and there, and then basically say, if there's no trade-off, I'll have a line that is parallel to this, only it's going to pass through the center of this cloud of data points. Asa?
What do you mean by trade-off?
A trade-off, we haven't really talked about, Dr. Reynolds will talk about it more. A trade-off is when you can't get something for nothing. So in this case, a faster snake is faster when it's not being affected by tetrodotoxin, but then when it's affected by tetrodotoxin, it's more affected than a snake that is slower. A more relevant trade-off to you guys is time. If you want to do well in school, what do you need to be doing? You need to be studying. But any time that you devote to studying, you can't devote to having fun. And if you decide that you're going to devote some time to fun, what are you trading off? Study time. And so that would be what's referred to in the literature as an allocation trade-off. You can allocate some resource to one thing or another thing, but because those two things are exclusive activities, you can't have an infinite amount of one and an infinite amount of another. To have more of one, you have to take away from the other. That's another kind of trade-off. This could be an allocation trade-off. It might also be a different kind of trade-off, and they're not sure which kind it is. But if there's no trade-off, this relationship should just be a straight line parallel to these that goes through this point, which is the average of the X and Y values. And so that is the dotted line. There's an effect of tetrodotoxin, but there's no trade-off. Does that line match the data very well? No. It looks like down here, we have a lot of positive residuals, very few negative ones. And up here, we have a lot of negative residuals and very few positive ones, which means that this isn't the correct slope. So we can run a regression analysis on these data, and we can calculate what the actual slope is. It's going through that point, this intersection, but you see that now the slope is less than 1. Therefore, that slope represents a trade-off because these fast snakes are affected more by the effect of tetrodotoxin than these slow snakes are, which is why it's dragging this end of the line down, which is why this best fit line has a slope of 0. This is a slope less than 1, and this line has a slope of 1 because this is the slope without a trade-off. So when you look at those figures look like this. The dotted line is the effect of TTX without a trade-off. The solid line is the effect of TTX with a trade-off. And the question is, in this case, not is the slope different from a slope of 0. In this case, I erased it already. The null hypothesis is that the slope equals 1. The alternative hypothesis is the slope is less than 1. And you can test this slope just this way you would test against a slope of 0. You're just saying that we want to know, is the slope that we observe different from a slope of 1? And so when you see things like this, don't let them wig you out. They're just plotting the slope of 1 so that you can visually see, is it likely that this slope is different from 1, lower than 1? Is this slope different from 1? Is that slope different from 1? And so they're using regression in lots of different ways in all of these papers. In some cases, they're using it to correct for body size. In some cases, they're using it to actually test their hypotheses about a trade-off. Regression you're going to find throughout these papers. So if you don't have some passing familiarity with regression, you're going to be lost, especially when they start referring to residual speed and things like that. So you need to remember what a residual is and how that works. Questions? Can you handle regression when you see it in the papers? That's all I have for you today. Dr. Reynolds, I assume you're not ready to take over yet? Yeah, I wasn't planning on it. I thought I might get finished a couple of minutes early. We have 9 minutes. I am happy to ask questions about this if you have them still. All right, next week we are going to be talking about, we're going to be reviewing quantitative genetics and talking about adaptive landscapes. That will be getting us ready for the discussion of the first Brody and Brody paper, which is next Friday. I will hopefully have your second set of literature summaries to hand back on Monday, so that at that point you'll now have feedback from 2 literature summaries to put into your 3rd literature summary. On that Friday, you have a literature summary. What? Oh.
She's laughing because I still haven't handed back the first.
No. My big thrill this Thanksgiving is going to be reading your literature summary so that we can get them back to you.
Some of you have asked me for a grade update. Go ahead and just